Hello, this is the pre-lecture video for the first half of Chapter 8. The concepts in Chapter 8 deal with chemical bonding. We will talk about ionic bonds and covalent bonds within this chapter. Some of the main topics will be things like lattice energies to describe strengths of ionic bonding, and Lewis structures to describe the structures of molecules or molecular compounds. So there are three basic types of bonds, two of which we talk about in this chapter. Ionic bonds are the bonds present in things like KCl, KNO3, any type of ionic compound. So this deals with the ionic attraction of cations and anions. Covalent bonds are those that are present, the types of bonds present in molecular compounds where we have electrons being shared among atoms. So we have such as the single bond between two H atoms and an H2 molecule, or the OH bonds between H and O atoms in a water molecule. And of course there's plenty other examples. Now metallic bonds are the bonds present in things like sodium solid, iron solid, aluminum solid, etc. There are bonds that are holding metal atoms together within their solid structures. Metallic bonding is described in a bit more detail in Chapter 12. We're not going to talk too much about metals in this chapter, but they are held together by what's often called the sea of electrons model, where we have a lot of valence electrons that end up getting shared by all of the nuclei, giving metals a different set of properties than ionic bonds, which are cases where you have plus and minus charged ions, so really no sharing of electrons at all among the atoms. And then covalent bonds, you get sharing but between distinct nuclei. So metals are described by having a almost complete sharing of electrons by all of the atoms. Ionic are really no sharing at all of electrons. You just have plus and minus charges develop. And then covalent bonds where you have specific electrons being shared among the atoms. One of the simplest ways to try to summarize an atom is to write its Lewis symbol. If we try to write the Lewis symbol for something like carbon, we might try to describe the valence electrons around carbon. We have a 1s2, 2s2, 2p2 configuration. Now we're going to neglect the inner core 1s orbital and just look at the valence electrons. So we generally want to depict the valence electrons because those are the electrons that are going to participate in bonding with other atoms in their valence electrons. And so here we have a Lewis symbol for carbon. Oxygen might look something like this. Neon might look something like this. So having 8 valence electrons often leads to the octet rule, that atoms are often trying to gain, lose, or share electrons so that they can obtain a noble gas count of electrons. And I think the noble gas count, usually it's 8, but it could be 2. So if you look at something like CH4, you have hydrogen obtaining its nearest noble gas count of electrons of 2, like helium. And you have carbon obtaining its nearest noble gas count of electrons of 8, like neon. So generally trying to get a noble gas count of electrons is how a lot of atoms behave when they make compounds. And some compounds will do that through sharing of electrons, and others by losing electrons. So sodium and chlorine, if they didn't share their electrons, would have 0 charges. Instead, chlorine has a very high likelihood of taking an electron. It makes chlorine more stable to take the electron and leave behind the positive charge. So sodium has the neon core, so it now has 8 valence electrons of neon, and then chlorine now has the argon configuration with 8 valence electrons as well. So from Chapter 5, the standard enthalpy of formation of NaCl is less than 0. It's about minus 410 kJs per mole, approximately. So if you take sodium and chlorine, bring them together, allow them to react, you get a violent exothermic reaction where NaCl results, with Na and Cl resulting. And so you can sort of think that sodium, there's an energy it takes to separate it from the solid lattice, to separate all the sodium atoms. Then there's going to be an energy it takes to ionize the sodium. Those are all positive amounts of energy. So you can think sodium solid has to separate itself into gaseous atoms. Then the gaseous atoms have to lose an electron and that's going to take energy as well. That's the ionization energy. This is the sublimation enthalpy, the enthalpy it takes the solid to sublime into the gas phase. And then likewise, Cl2 has to, it's already a gas, so it doesn't have to sublime, it's already a gas, but it does have to break the bond to chlorine. Then the chlorine atoms actually lose energy upon going to chloride ions. And then the gaseous chlorine and sodium ions, once they're formed, can then form a bond together and then form NaCl. And NaCl is stable because you get the plus and the minus electrostatic attraction as they start to solidify into the solid state. So we're going to describe something called a Born-Haber cycle in a minute, but the idea here is that sodium chloride is forming very exothermically because you have the formation of a very strong ionic bond. So ionic bonding occurs with metals that have low ionization energies and nonmetals which have favorable electron affinities. So cations form with the least amount of energy required, and then anions form with the most amount of energy returned. And then once these ions form, you then get the solidifying and the electrostatic attraction of those ions together. Through Coulomb's law, we know you get an attraction of oppositely charged particles. So the electrostatic attraction then takes us the rest of the way to a stable solid compound. So then you get something like NaCl that forms as a solid with a melting point over 800 degrees C. So a very high melting point indicates a very strong attraction of those ions. So some of the properties of ionic solids include that they're brittle, so you can sort of break the structure at any point along these plus and minus charges because there's really not much holding the entire structure together, so you get a brittle solid. If you had sharing of electrons across this entire lattice, then that would make the structure much more strong and not as brittle. That would be the type of structure in like a diamond lattice. So diamond, very strong because we have all the atoms linked together by electrons that are being shared among neighboring atoms and become kind of the glue to keep that structure held together. Now, you have electrostatic attraction, but you can break that attraction fairly easily just with, say, a hammer and breaking up a salt crystal. So you also get high melting points. That's just because of the nature of that electrostatic attraction. You tend to form crystals. And one of the ideas of a crystal is that you get a perfect pattern, so you get some brilliant properties, like they reflect light very similarly, so you get, at least in the case of a polished crystal, a very reflective surface. So we started this discussion off about NaCl by pointing out that the enthalpy of formation of sodium chloride in the solid phase is negative. And so that means that the reaction is solid sodium and a half Cl2 in the gas phase, forming NaCl solid. That reaction is the definition of the enthalpy of formation reaction from chapter 5, and it has a delta H of about minus 410. So it's approximately 410 kJs per mole. So now, why is this negative? Well, if we think about the energy it takes to take solid sodium up to gaseous sodium, that's the enthalpy of formation of solid, of the gaseous sodium gas. So let's see how we can calculate this quantity here. So if we were to take sodium solid and convert that to sodium gas, that would be the delta HF of sodium gas. Since the enthalpy of formation of sodium solid is 0, then we would add the ionization energy of sodium gas to sodium plus an electron. In chapter 7, all of those ionization energies for like sodium and for potassium, all the ionization energies given are for the gaseous atom. So this is the ionization energy of sodium, and then the Cl2, half mole of this substance has to break that bond to form Cl atoms. So half a mole of chlorine has to break the bond to form a mole of chlorine atoms. that energy is the 1/2 of the bond dissociation energy, or the bond enthalpy. Maybe we'll use the symbol D. So we use the symbol D to symbolize bond strength. So it's about half the bond strength of the Cl-Cl bond. And that's from chapter 5. And then chlorine absorbing an electron to go to Cl-. Now that's negative. That's the electron affinity of chlorine. So we have the ionization energy of sodium, the electron affinity of chlorine, and then once we form the have the ions formed of sodium gas and chlorine gas, and they can solidify and form that solid lattice in terms of NaCl solid. Now this reaction here is an important one. We call this reaction here, or actually we would call the reverse of this reaction. If we look at the reverse reaction of sodium solid converting into its gaseous ions, that this reaction here is defining what we call the lattice energy. So the lattice energy of sodium chloride is the energy it takes to take a mole of the ionic compound and separate it into its gaseous ions. So this reaction here then ends up being the lattice energy but backwards. So this reaction here is minus the lattice energy. And so sodium gas, chloride gas then form an exothermic reaction. Exothermic here because you get the electrostatic attraction of the plus and minus ions. So this drops in energy forming sodium chloride, where then you get a net negative delta H. So we could do a few things here. Like if we knew the lattice energy of sodium chloride, and we knew the electron affinity of chloride, the bond strength, the ionization energy, the delta HF of sodium, that should be sodium gas. Let me rewrite that. It's kind of messy. So that's sodium gas. If we know all of these things, then we can solve for and determine the delta HF of sodium chloride. We could also say, well, we already probably knew. We could check this number in the appendix of our textbook. We can use these types of equations here to actually solve for and determine the lattice energy. So the lattice energy relates to the strength of attraction of the plus and minus charges in our ionic compounds. It's not something we can directly study in the lab, so we're not going to come up with any experiment that furnishes a lattice energy. We have to instead take a bunch of other lattice energies, or a bunch of other delta H's, if you will, that we could rearrange, use Hess's law, sum them up to solve for a given lattice energy. Okay, so a lattice energy is positive. If you separate the ions, it takes energy to do so. And then the amount of energy it takes is then dependent on a few properties of the ions. So if you were to look at the lattice energy of MgO compared to NaCl, MgO's is a lot higher because you have double charged ions compared to NaCl. So it's going to take a lot more energy to separate higher charged ions because we have this relationship for the electrostatic attraction is directly proportional to the two charges divided by their distance of separation. So if you make these charges higher, then you're going to make the electrostatic attraction higher, more energy required to separate the ions. If you also compare to, say, making a smaller ion, if you compare NaCl to, say, LiF, where lithium is smaller, fluoride smaller, you actually strengthen the attraction of the ions because they're closer together. So make these ions smaller, greater energy required to separate them compared to NaCl, which has larger ions, so they're a little bit further away, so it's going to take a little bit less energy to separate the ions in NaCl. So we can understand some of the trends of strengths of ionic bonds by just simply understanding the nature of the formation of ionic compounds and the relative lattice energies that their ions have with each other. So the lattice energy is defined as the energy required to completely separate 1 mole of a solid ionic compound into its gaseous ions. So ionic compounds, usually solids at room temperature. Their ions usually, we want to consider them to be gaseous ions, so we get a sense of how attracted those ions were to each other. So the that amount of energy is released to make the ionic compound. Oh, that amount of energy is the energy that's released when we make the ionic compound. Okay, so when you have NaCl breaking apart into sodium gas plus chloride gas, this delta H is defined as the lattice energy, positive quantity 788. The energy being released was that when we have the chloride and the sodium ions coming together to make NaCl, that we then would have the delta H being, for this reaction, minus 788 kJs per mole of NaCl. So when we're making our solid ionic compound, this is the energy that's released upon forming the compound. Then once we have the compound, it's energy that would be required to separate those ions back into their gaseous state. So this table here is showing a summary of some different compounds' lattice energies. So let's compare LiF to Cl to I. So we have fluoride, chloride, iodide just simply growing in size. Look at the lattice energy dropping. So LiF has the greatest lattice energy because the ions are the closest together. So you have Li is the same size. So you have the same size plus ion. You're just going from a small minus to a bigger minus to a bigger minus. So weaker attraction as the ion grows larger. Same trend, NaF to Cl to Br, dropping in the lattice energy with the increasing size of the ion, increasing the distance of the separation of those ions. So if we were to look back at our electrostatic attraction equation, our electrostatic attraction is related to the Q1, Q2 divided by D. So in order for the attraction to be net attractive, you have to have a plus or a minus or a plus ion, so oppositely charged particles. And then if you bring those particles closer together, you then increase that attraction of those ions. So bringing the ions closer together, like an NaF, increases the energy it takes to separate the ions. Likewise, in the case of Kf through Kbr, exact same trend. So no deviations in the trend. A drop with the increase in the size of the ion due to the increase of the distance of separation of those ions. Now, when we compare like MgCl2 to strontium chloride, here we have magnesium increasing in size, we get a dropping in the lattice energy. Same thing with MgO, calcium oxide's a bigger calcium, strontium's a bigger metal, we get a drop in the lattice energy. Okay, now notice something else, like if you go from NaF to MgO, you're going from +1, -1, to slightly smaller, but look at this, the size of the small. Like decreasing the ions have a relatively small change in the lattice energy compared to going to a 2 + 2 - versus a +1 - 1 has a dramatic increase, almost by about a factor of 4. So if we go from plus minus and then double the magnitudes of charge on both of those ions, then that results in about a quadrupling in the lattice energy. So the lattice energy of MgO is about 3,800 kJs per mole, whereas it was only about 900 kJs per mole for NaF. And then in the case of strontium chloride, it's about double because we have a +1 - 1. We actually have two of the bonds we're breaking too. So in strontium chloride's case, you have a +2 chloride and another chloride over here. So you're actually breaking two minus +2 charges. So you get an increase in the lattice energy of each of those bonds by about a factor of 2. And so then you get a higher lattice energy for a 2 ± for the case like strontium and magnesium chloride compared to their +1 - 1 counterparts. Okay, and then likewise, if you have a +3 - 3, it almost increases by about a factor of 9 compared to roughly the 800, give or take, lattice energies for +1 - 1s. So we get a lattice energy of 7,500 for scandium nitride. Now, there's not many examples of nitride, so there's not a whole lot of examples of things like this. And we don't have any 4- ions that routinely form, so -3 would be about the biggest ion that we see in the case of the anions. So an increase in lattice energy with the increase in the charge magnitudes, and then a increase in the lattice energy with a decreasing size of the ions because we're getting closer together. So here's a slide summarizing the trends. We can relate the electrostatic attraction to Coulomb's law, where the electrostatic attraction is kappa Q1 Q2 divided by D. And so as the charge magnitudes increase, the lattice energy increase. So the lattice energy increases as the charge magnitudes increase. So the charge magnitudes of those increase. Then we get an increase in lattice energy. Then our lattice energy actually drops when we get an increase in size. So if we increase size, we increase the distance of separation of the ions, we therefore decrease the lattice energy. So again, we see lithium chloride to cesium chloride increasing the size of the alkali metal leads to a decrease in the lattice energy. The same thing when we increase the size of the halogen ion. So let's shift away from ionic bonding and talk about covalent bonding. So let's think about perhaps hydrogen. So the H2 molecule has one proton in each of the nuclei of the H atoms, and then 2 electrons. These electrons can then spin around the molecule. We'll actually see later in chapter 9 that there's a molecular orbital that can contain these electrons so that they can spin kind of in one direction around the atoms or in the opposite direction around the atoms, and you form these types of molecular orbitals. And so then you get the greatest probability of finding the electrons between the 2 nuclei, smaller probability away from the nuclei, but most of your probability is right in the center of your 2 atoms. And so you have the 2 negatively charged electrons, they repel each other, but they're attracted to the nuclei. So each of the electrons experiences attraction to the nuclei. The nuclei themselves repel, the electrons themselves repel, so you can't get these nuclei directly on top of each other due to those repulsions. The bond length of an H2 molecule ends up being about 0.75 angstrom. Is about as close as you can get those 2 nuclei where they reach that perfect spot in terms of their bonding. You can describe this bonding through like a potential energy curve. So you have 2 H's coming together to form H2 in the middle. If you keep compressing the H2, then the energy eventually goes back up. So the energy here is about 436 kJs per mole. That's the bond energy of the H2 bond. So we're going to drop down by 436 kJs per mole compared to 2 separated H's, or if you have an H2 molecule, it would take the absorption of 436 kilojoules per mole of H2 to break that bond. So the electrons are forming bonds here. Now if you compare this to the bond strength of an ionic bond, which is about 800 kJs per mole, give or take, that covalent bonds are generally a little bit weaker, about half the strength of ionic bonds, so they're not as strong as ionic bonds. Now the way we describe molecular compounds are through their Lewis structures. So you have H share the electron between the 2 through a single bond. Same thing with Cl2, except you have 7 electrons in each of the Lewis structures for chlorine, 7 valence electrons. So with a single bond, you give each of the chlorines a total of 8 valence electrons. So you're satisfying the octet rule for chlorine this way. For HCl, you compare chlorine up with hydrogen. So hydrogen gets its 2 electrons like helium, and then chlorine gets its 8 electrons like its nearest noble gas of neon. So let's take a look at the compounds of HF, H2O, NH3, and CH4. So of course we know that these are all the stable molecules: hydrogen fluoride or hydrofluoric acid, water, ammonia, and methane. And so when we inspect or kind of think about oxygen having 2 valence electrons, so making 2 single bonds, leaving behind 2 sets of electrons. Nitrogen, kind of similar, Lewis structure for nitrogen. It has 1 extra valence electron, so it pairs up with 3 H's. And then CH4, we can actually distribute a valence electron of carbon to each of the corners of carbon, so we can get 4 single bonds to 4 different hydrogens. So now, why do we not form a stable molecule with 4 H's around nitrogen? Like, why don't we get an extra bond? Well, we're kind of capped out at nitrogen once we reach the total of having 8 electrons surrounding nitrogen. Same thing with carbon. We have 8 electrons surrounding carbon now, so that's its maximum. Same thing with oxygen. Another property we can calculate for the atoms is their net charge once they're in the molecule. So the net charge an atom bears, we can calculate by taking, so hydrogen has 1 valence electron. In this structure, it's surrounded by 1 electron. So it has a net charge of 0. For the fluorine, it has 7 valence electrons, and in this structure, it has 7 electrons closest to it. So you're kind of like putting cutting the bond in half, and then saying how many electrons are closest to one atom, how many closer to the other. So there's no net charge on the fluorine atom of HF. And the same thing with oxygen. So if you look at the H's here, they're all going to be 0. In all of these molecules, it's just 1 minus 1. Let's look at the case of O. So draw the box around O. We only have half the electrons in those bonding pairs close to oxygen. So for O here, it should have 6 electrons. That's its valence count. And then it's surrounded by 1, 2, 3, 4, 5, 6 electrons. So the idea is if oxygen has 6 valence electrons, it has 0 charge. If it has more valence electrons around it now, then it would have a negative charge. If it has fewer valence electrons, it would have a positive charge. So its charge is 0. Nitrogen, 5 valence electrons minus 5 electrons surrounding it gives it what we call a formal charge of 0. Carbon, likewise, also has a formal charge of 0. 4 valence electrons minus 4 surrounding it equal to 0. So formal charge is the representation of charge of atoms that they bear, assuming the equal sharing of electrons. Now we should talk more about whether bonds are truly shared equally or not, but the idea of formal charge is that it allows us to try to look at the charges of atoms and see that in a lot of cases for stable compounds, they have all of their atoms situated in a way that their formal charges are 0, and usually, but not always, the octet rule gets satisfied in the same process for the atoms. So we'll go through a systematic set of rules for drawing Lewis structures for some more complicated molecules, but in these ones here we're seeing satisfaction of the octet rule for these atoms, and also their formal charges are 0, in that these are common examples of some stable molecules. Okay, now let's look at the case of multiple bonds. So if we're going to make a multiple bond between, or if we're looking at CO2 in general, if we make only a single bond, then what we'd be left with is 2, 4, 6, 7 electrons surrounding each oxygen, and only 2 plus 2 plus 2, only 6 electrons surrounding carbon. So we have none of the atoms satisfying the octet rule. So what we might do is make a multiple bond. So we might make a bond here, then we might do that one more time, so we can satisfy the octet rule for carbon and oxygen. And then once we do so, we can do the same formal charge rule, cut those bonds in half. There's some equations in the book. I think they're silly. Just literally draw a box, break the electrons in the bonding pairs in half, and then carbon, 4 valence electrons surrounded by 4, net 0 charge. Oxygen, 6 valence electrons minus 1, 2. Oh, let me get my pointer here. So we have 1, 2, 3, 4, 5, 6 electrons surrounding each of the oxygens for a 0 formal charge. Now I can write these zeros in. Usually I don't when they're 0. I mean, we can, but it's not exactly necessary to indicate 0 formal charges. Same thing for, or when we look at nitrogen. So nitrogen can form a triple bond. So we get a triple bond between 2 nitrogen atoms. And then again, we have the satisfaction of the octet rule, 8 electrons around each end, and then 5 valence electrons for nitrogen minus 1, 2, 3, 4, 5 for a 0 charge. Like O2, the bond in O2. So 2s2, 2p4. So we get a double bond. And then we also have the satisfaction of 0 formal charges for both O's and O2. So let's take a look at bond polarity. So bond polarity is a measure of how equally or unequally the electrons are shared in a covalent bond. In a nonpolar covalent bond, the electrons are shared equally. Now there's some easy examples of covalent bonds. If both the atoms are the same, like in F2, both of the atoms are identical to each other. They both have 0 formal charges. Neither nuclei is pulling these bonding electrons closer towards its nucleus. So you can think of each F as trying to fight over these electrons, and it's an equal tug of war. So those electrons will be equally shared among the 2 F atoms. So this is a perfect example of a nonpolar covalent bond. So your examples of nonpolar covalent bonds are just atoms that have a similar desire, or in the case of the exact same atom, an equal desire for electrons. So a diatomic molecule where both the atoms are the same, like O2, fits this category as well. Both the atoms of O are exactly the same in this molecule, and so neither O can pull the bonding pair electrons any closer towards itself. So the molecule of O2 would be defined as a nonpolar molecule because it has one nonpolar bond. So in a polar covalent bond, one of the atoms attracts the electrons closer towards itself with a greater force. So if we think of HF as an example, so we can draw the Lewis structure very easily. So one electron in the Lewis structure is closer to H, one closer to F in terms of the Lewis structure. Formal charge says, assume that that bond's perfectly, and equally shared. But something about F that's much different than H is its effective nuclear charge. Fluorine has a really small nucleus with a really positive charge. What that's going to do is it's going to take these negative electrons and pull them more closely towards the fluorine. So fluorine develops a negative charge, hydrogen develops a positive charge. The symbol delta implies it's partial. Now what we mean by partial can be described if we consider fully ionic for a minute. If this bond were perfectly polarized, then it would be ionic, with the electron going all the way to F, and then losing the electron completely off the H. If this were to happen, you can think about the bond here, the bond order would kind of disappear. There'd be no bond other than the ionic attraction, so there'd be no covalent bond anymore. The full charge of F would be -1. The charge on hydrogen would be +1. So -1 electron plus 1 electron. Now the partial, what this means is we get somewhat of a negative charge, not fully -1, but also not 0. We can calculate this a little bit later, but we're going to see that this, is somewhere between 0 and 1 electron. And then in the case of F, it's minus somewhere between 0 to 1 electron. Then the H would be somewhere between 0 to +1 electron. So something like F2, each of the atoms has an equal pull of the electrons, no net charge on one side of the molecule. HF has a pull towards the F atom, so the F atom's going negative, the H atom's going positive. Red's showing a picking up or more of a negative charge being developed on the F atom. And LAF, it's even more pronounced, where we get the full plus, the full minus. We're having an actual ionic compound with +1 electron, -1 electron. So partial negative for F and HF, partial positive, fully +1 for Li and LAF. Now the difference here from chapter 7 is that the ionization energy of H is a lot higher than lithium. Lithium's ionization energy is only about 500 kJ per mole. Hydrogen's is over 1300. So hydrogen doesn't give that electron up as easily as lithium. So lithium goes full plus, fluoride goes full minus, and LAF in the ionic compound. We can describe the desire for electrons through the comparison of the electronegativities of the atoms. So fluorine has two things going for it. It has the highest possible effective nuclear charge of the nuclei that form bonds. So if you notice here, you don't see the noble gases. So you don't see neon or helium or the other atoms because they're not forming bonds. So electronegativity is a property of atoms in bonds. So we don't see the noble gases within this property. So for the atoms that form bonds, the halogens have the highest effective nuclear charges, and then fluorine's also the smallest. And so the smaller the charge, the greater the desire, the greater that nucleus can pull the electrons in towards itself. So electronegativity is increasing towards fluorine in both directions. So up a row and from left to right. And then you get some interesting behavior across the transition metal sequence. Nothing really to particularly memorize here. We get an increase and then a decrease through the noble gas series. But generally from left to right, you're getting an increase for your main group, your S and P block. Hydrogen's electronegativity is relatively low. It's worth pointing out that H is relatively low. So if you pair hydrogen up with like F, Cl, Br, or I, you form a polar bond. And so generally all you need is a difference of electronegativity in order to classify something as being a polar covalent bond. So as long as you pair two atoms up with a different amount of electronegativity for each atom, then the bond would be polar. Molecular polarity is actually a complicated issue that we're going to come back to in chapter 9. So whether or not a molecule with 3 or more atoms is polar, that's an issue we're going to have to come back to in the next chapter. For these small diatomic molecules, that the bond's polar for 2 atoms, you can look here and say, okay, this is a polar bond for a diatomic molecule. Then you can say it's a polar molecule. So for larger molecules, let's come back to this concept of molecular polarity in the next chapter. Now, one thing that's kind of interesting for small molecules, you can do this for larger ones too, but it's much more complicated. But for diatomic molecules, we can actually calculate and then relate a dipole moment relative to the charges and the bond length that separates those charges. And so a bond length, a dipole moment for a diatomic molecule, so just 2 atoms exactly in our molecule, we can calculate our dipole moment by calculating the charge on one atom compared to the charge on the other atom. And so Q is just the magnitude of this charge that's separated. Now, one thing right off the bat, if you have F2, the charges are 0. Each atom is exactly 0. Plug a 0 in for Q, no dipole moment. So for a non-polar covalent bond, the dipole moment would be 0. But the value of the dipole moment should be proportional to those charge magnitudes. So you make those charge magnitudes bigger, the dipole moment goes up. And actually, if you increase the distance of separation of those atoms, the bond length goes up as well. Okay, so let's try to calculate a dipole moment for something like HF. Because the only things we really need to know for HF, or let's maybe try to calculate Q for the charges on H and F and HF, given that our dipole moment is experimentally determinable. You can determine this through experiment, and you can also determine the bond length through experiment. So these values here, you can experimentally determine these, so then you can solve for Q and understand what Q is for atoms and different types of bonds. So now for HF, the dipole moment is equal to 1.82 capital D. That unit stands for Debye. And then the bond length, or the bond length is wrong symbol. The bond length is R. And for HF, that's 0.92 angstrom. Okay, so can we solve for what Q is? Well, we just have to do a couple conversions. So 1 Debye, it's actually a non-SI unit for dipole moments. The SI unit of charge is coulombs. The SI unit of distance for a bond length is meters. So the conversion of the non-SI unit Debye into the SI unit coulomb meters is 1 Debye is equal to 3.34 times 10 to the minus 30 coulomb meters. Okay, now this is always a given. Like, this is kind of a weird value. So if you need this on a test, you'd have this given to you. And so what we might do is if we're trying to solve for Q and say, well, what is Q on HF? Like, how negative is the charge on F? How positive is the charge on H? Well, let's just take Q. Let me actually move this over a little bit. So let's take Q equal to the dipole moment divided by R. Now the only tricky part is we have to account for some units here. We can't just do it simply as 1.82 divided by 0.92. We can start with that. Like, we can write 1.82 Debye divide by 0.92 angstrom, and then just worry about our conversions. Like, let's do the conversion of 1 Debye is 3.34 times 10 to the minus 30 coulomb meters. And so then that says we want the angstrom to go to meters. 1 angstrom is a 10 to the minus 10 meter. So if we work that out, and so we work out the math here, this comes out to 6.61 times 10 to the minus 20 coulombs. Now, at first glance, that's kind of complicated because you're saying, well, that's a really small charge. And it is. The issue, though, is that this is the charge of one of the atoms in one molecule. So when we say the charge could be as high as +1 and -1 electron, if it's fully ionic, we're saying, you know, it's minus the charge of an electron plus the charge of an electron. The charge of one electron is 1.602 times 10 to the minus 19 coulombs. This is also generally a given. Now, you may have seen this before. This may be a more likely number that you already know or have seen in the past, but this is the connection where if this charge here had come out to 1.6 times 10 to the minus 19 coulombs, then that would be a charge of plus and minus 1 electron. Now you can see it's less than this. The charge on H and F is a little bit lower in magnitude, and we can just do the conversion. 1.602 times 10 to the minus 19 coulombs per 1 electron to get the electron charge. So we calculate our electron charge just by dividing by 1.602 times 10 to the minus 19, and we obtain 0.41. If we're counting sig figs, we only have 2 here, so 2 here, so 2 to here. So the charge on F and HF would be minus 0.41 of an electron, and then the charge on H would be about plus 0.41 electrons. So it's almost about halfway ionized. So sometimes we describe this by the percent ionization, that this is about 41% ionized. F2 would be 0% ionized. A covalent exactly shared electrons would be 0% ionized. This one here, if it's 100% ionized, would be 1 electron. So this is about 41% ionized at this point here. So if we get all the way to 1 electron, then that would be 100% ionized. So let's compare HF to HCl to HBr to HI. So the bond length is growing. Now in our equation, mu is equal to Q times R. As the bond length grows, we saw that the dipole moment could grow, but the charge magnitude is going to drop because the electronegativity difference is dropping. The electronegativity difference plays a much bigger role here, and we see the dipole moments dropping in the molecules as the bond length's growing larger, but then the electronegativity difference between H and Cl and Br and I is dropping. So the electronegativity difference, this plays the biggest role in determining Q. So we get the biggest charge separation in HF, we get the lowest charge separation in HI, so we get the smallest dipole moment in HI. So you get a better connection between mu and the dipole moment to the relative electronegativities of the atom. So generally, the greater the electronegativity difference between two atoms, then the greater the polarity of the bond, the larger the dipole moment of that bond. So is a compound ionic or covalent is sometimes a question that you may have. A simple approach, and this is the one I would recommend, is that metals and nonmetals form ionic compounds, and then nonmetals with nonmetals form covalent compounds. And then most likely if the atoms are different, it's going to be polar covalent if you have two nonmetal atoms. Now, if you look at your electronegativity differences, some books say, well, if the electronegativity difference is less than about 2, then you may classify that as being covalent. That's going to lead a lot of metal nonmetals to being classified as being covalent. I think it's best just to think metals and nonmetals are going to most likely form ionic compounds. Some metals may end up forming some types of covalent bonds, but I don't want to blur the lines too much and get too caught up. One of the things you may think about is that properties of compounds are often a better way to compare. So the lower the melting point of a compound, the more likely that compound has just covalent bonding. Whereas the higher the melting point, that's probably going to indicate more signs of ionic bonding. So look at HF. At room temperature, it's a gas. HCl is actually a gas at room temperature. Yeah, you can dissolve these things in water, but their natural states are gases for all of these. So all of those are gases at room temperature. Lithium fluoride, sodium fluoride, or, KBr, all these salts are solids at room temperature, have very high melting points. So when you look and say, okay, we do get some positive charge and some negative charge, it still leads these compounds to existing as gases at room temperature and not having the same type of strengths of attraction as the fully ionized atoms in the case of ionic compounds. So metals and nonmetals generally are going to have higher melting points when they're mixed together. If you find a metal and a nonmetal compound with a relatively low melting point, probably indicative that it's more of a covalent type bonding nature between its atoms than the ionic nature that we see in common ionic compounds. So covalent bonds are polar when their atoms differ in electronegativity, and so that's just about any atoms that differ in electronegativity, except for some of the really not so polar atoms. So like H pairing up with carbon or boron, and some of the more central nonmetal atoms are going to lead to not a great electronegativity difference, whereas if you pair H up with the halogens or the oxygen group elements, those are going to lead those bonds to being polar covalent in their natures. Well, that wraps up this pre-lecture video for the first half of Chapter 8. We'll talk more in the next video, in the next lecture, on actually determining Lewis structures for a wide variety of different types of compounds. So let's look forward to that in the upcoming video. All right, thank you for the attention.